Hello everybody. Last we had talked about effective change of density. Today we'll just continue a little further and see how it is used practically, how it's achieved. So one of the things what we had talked about that when there is a change of density, and if the draft remains constant, then the displacement would change, and that I had talked to you in this video here. So let us see how it works, and this is what I had shown you there that if two rectangular boxes were displacing equal amount of water in two different densities, then we had worked out that the displacement had changed from 1000 to 976. As we know that the Archimedes principle talks about floating of vessel displacing its own weight of water in water. Now here I'm just going to be using these symbols for displacement and for densities. So let me just call that the rectangular box here or a ship is in this density here. I'm calling it old because now from here it is going to proceed to the density of new density, water of new relative density or specific gravity or density here. So I'm calling it a old displacement and old density here. And we know that mass per unit volume is density. So mass is basically the volume of water what is displaced multiplied by density or relative density, specific gravity. So what is the volume displaced? Volume of water displaced is mass divided by the density. I'm just calling it the new displacement when this ship has moved from the density of rho 1 to rho 2. Draft remaining constant. So we had seen that displacement would change. So I'm just calling it a new displacement here in new density. And same thing here, it works out that whatever the mass divided by the density would be the volume of water displaced. Now that we know that we can see that the drafts are same, so the volume of water displaced must be the same. If we are talking about a rectangular body here, length and breadth is same, and draft also same. So definitely the volume of water what is being displaced is the same in both the densities. So let me call this as volume 1 and volume 2. That means volume 1 and volume 2 underwater volume in both the cases is same. Now if you look at this equation here, if the densities have changed here, then definitely your weight would change so that we can have the same volume on either side. So if the density changes, the volume is the same, so the water displaced would be different. Now just equating these two, I get it like this, and the relation what we get is old displacement divided by new displacement is equal to old density by new density. Now this old good for ships. So let us see how do we put it to practical use of it. See, we have hydrostatic tables for a ship on board in which all these particulars are given. So today I'm just going to be talking to you about draft and displacement. We had talked about TPC, the change in TPC also earlier. We'll get back to this, and the rest of the things will follow soon. So assuming that the draft in salt water is, and I want the same draft in relative density. So how do I proceed? First I try to figure out what is my displacement for this draft in salt water, and that is a question of interpolating here. But for 3.8 it is there, 4 is this, so I'm not going to explain that part of it, and you get to know that your displacement in salt water is about 7,500 metric tons. Now we just saw that underwater volume, whatever the volume is there, is mass over the density, mass divided by density, so that we get underwater volume. When we are asking for having same drafts in both the densities, that means the underwater volume will be the same in both the densities as the draft is same. And what would be the displacement? What would be the thing? It will be mass into mass would be equal to volume into density. So this is how I calculate my displacement when the ship goes from one density to another. So let us just make use of the relationship what we just found out and figure out, do some questions there and see how it works out. So now this is one of the questions here. It talks about that ship is in the relative density of 1.025. That's the displacement, and is to proceed up a river with a relative density of 1.018, having the same draft. So as the relation what we saw, so just substituting the values there, I get what is my new displacement. The old displacement is already given to me as 12,000 tons. So the difference between this would be the cargo what I'm discharging. Now this question, if it was to be done practically, I mean, you will not be talking in terms of it. You'll just say, okay, your ship is at a draft of 6 meters, and you want the same draft to be maintained when you are reaching the relative density of 1008. So you will go into the tables, look around what is your displacement in salt water, get the underwater volume displaced by dividing it by density. And when you are asking for that the draft are 6 meters in a particular density, so 6 meters in the density of 1024 would be displacing, because underwater volume is the same in salt water and in this density, would be underwater volume into density. So this would be the displacement in 1024. Now it is remaining the same in 1001.008 here. So underwater volume still the same for 6 meter, and the displacement would be multiplied by the relative density here. And the cargo discharge, the displacement here minus this, and that is what we had seen obtained here. Of course, it's not the case here. I've just made up this question here. So this is how you'll do it out at sea. Just figure out the displacement of salt water, find out the underwater volume, convert it into displacement for the density what has been asked for 1024 or 1.024, and then for the next relative density here. Another question here, in fresh water to a salt marks goes to another port consuming 20 tons of bunkers. That's the relative density in the second boat, and 120 tons of cargo have been loaded on the ship. So if we just put the relationship what we saw right in the beginning, what is the displacement when it is reaching the second port, whatever was there in fresh water, minus or plus. So now in this case we have loaded and we have consumed, so the additional weight is 100 tons here. So the new displacement in this would be whatever was there in fresh water plus 100. I'm just putting up these values here. I get what was my displacement in fresh water. This was my displacement in fresh water. Now he wants me to find out the ship's load displacement in salt water. So divided by 1 is your underwater volume multiplied by the density gives you the displacement in salt water here. This question here is talking about that the ship is in relative density of this. It is discharging, consuming, and reaches the second port of 1.004. And again, its freeboard is the same as this. That means your draft system is the same. So S is basically for summer freeboard. So I just put up the thing, old displacement, new displacement, the formula here. What is my new displacement here? Whatever was my displacement here, and now I have discharged both the thing or consumed. So minus 164. And solving this, I get my displacement in relative density of 1.016. And what would be my arrival? Would be whatever my density, whatever my displacement was here, minus what I have consumed, and this. This I have done it another way with underwater volume, whichever you are comfortable with. I sometimes find that this is more comfortable because I tend to forget that formula. So I just remember that volume of water should be the same if their drafts are same. So I find that this is a little easier way. So it is up to you whichever way you want to do it. So I have just assumed that the displacement in 1016 is delta. The volume of water displaced would be this mass over density. He says in our arrival, the displacement is going to be what? Whatever the displacement was there in 1016 minus 164, as 150 and 14 tons have been discharged or consumed. So volume of water displaced in 1014 would be the displacement divided by 1014. Now arrival in 1014, they both have the same drafts. So the volume of water displaced in both of them would be equal. And 1.016 relative density, the underwater volume would be this. The volume on both the sides, as I said, the drafts the same. Underwater volume will be the same. And I work out and get my displacement in 1016 here. What will be my arrival? Minus 164. So either way you can do it, whichever you prefer, whichever you find easier. Now this same question, I've just changed it a little bit if it was to be done up in practical thing, because I would know my drafts. So I would say, okay, she's on the same draft again. As I said, freeboard, same freeboards. Just how much cargo should be loaded or discharged before I reach the next port with the same draft. So I look into my tables that basically my summer draft is this. So whatever my freeboard is going to be, the from keel to freeboard minus summer draft, but that is good. That I'll come back to it later. But here it is given to me that summer draft is this. So I go into the tables, and here both the displacements are 6 and 7 6.8 and 7 is given, and then I try to interpolate for this draft what is given here, and that is my displacement. So what is the underwater volume? As I said, mass divided by density is the volume. The mass of underwater volume in this, because this I have found out in salt water. So in this relative density would be underwater volume into the density, relative density. In the other relative density again, the drafts the same, so underwater volume will still be the same. The mass would change, multiplied with the density, and you got the mass of underwater volume. And the difference between these two would give you the cargo discharged or loaded. And that is what we see here, that the amount is nearly the same as this. So it is up to you how you want to do it. As I told you earlier, with the formulas or like this. This is the practical way of doing it out at sea, because I'll be knowing my drafts there rather than knowing my displacement. Now, in the last topic, when we had talked about the effective change of density, we had seen that if the displacements were same, then the draft would change. So far, we've been talking about the draft was same, so the displacement was changing. But now here, if the displacement is the same, draft would change, and we had worked out this relationship here. Then this relationship is good enough for a rectangular box, because here length, breadth, and height, no variation, but not applicable for the ship, because the ship is not shaped like a rectangle. Today we talk about freshwater allowance. So this will be my next topic. Till then, thank you for being with me. So I'll be talking about freshwater, dock water allowance in my next lecture. Till then,